So first of all, let me thank the organizers and in particular Rickard for contacting me to present a talk about our organic materials database. I'm actually very happy to present in this community because I think it's actually the right or perfect network to contact or like to connect. Let me mention up front, like it's probably one of the reasons why I was also invited is that right now we don't use the Optimate framework. So just to kind of address the elephant in the room up front. But anyway, I think it's quite interesting to just, you know, present you a bit what we have and why we started this database and kind of what sort of fields of research we are interested in. And then maybe go from there and see like how we can set up a discussion about our framework and about your framework and yeah, how things can evolve. So this is like our, just to show, this is our link on db.mathhub.io. I will actually show you some examples of our webpage in a second. But let me start with just acknowledging other members in our team. So we are actually a fairly small project. The whole project started in 2016 when I came to DITA. And it was pretty much the same time when also Stanislav Borisov started at DITA. So both of us were postdocs at the time. And we are kind of working under supervision of Alexander Balatsky, who is the PI of the condensed matter group here at DITA. But it's a quite broad group. So this like materials informatics perspective is pretty much only one angle of the research lines that we are interested in here. And then during the years, we had a couple of other guys coming in particular Johan Helsvik, who is now working on the magnetic part of our database as a postdoc, and also Bart Olstron, who is a PhD student who actually did kind of significant work on this project. And other than that, we actually mainly had student assistants on the master's level kind of pushing this platform. And it's like with quite limited resources, I actually guess we got pretty far at the current stage. So let me just you know, outline a little bit of the kind of why we actually started this and what sort of materials we are interested in here in our research at DITA. So there's this kind of huge field of the quantum materials, which these days is a bit of a buzzword probably, right? Like people just use phrases to mention that things are interesting. But what one can actually say about quantum materials is it's like materials where quantum effects are dominant or wide range of energy and length scales. And these sort of materials actually have a quite interesting and long history. And it already started like back in the day with the discovery of the liquid helium or the superconductivity, and actually kind of got a boost during the past decades. Like first after the discovery of high temperature superconductivity and about the like topological excitations in the fractional quantum Hall effect. And then it actually went on like recently to these what we now call Dirac materials, where you have materials where kind of elementary excitations effectively behave as a kind of fully relativistic Dirac particles. And also in this like realm of the spin liquids, where actually like the organic materials play a significant role. So just to give a bit of the like motivation why we are actually interested in the organic materials and what organic materials actually are. So I have to say, like, I'm a bit sloppy if it comes to the definition of organics. Like on the left, I just show you two pictures where the uppermost one is it like, let's say, typical example of a organic molecular crystal. So what you can see is like you have these nice organic molecules. So organic materials are materials which are kind of composed of carbon and kind of mostly hydrogen. And these molecules, they start to interact via some sort of van der Waals interaction and start to form crystals. And that's pretty much what people refer to if they talk about organic molecular crystals. But then there's a kind of another class of materials which I also incorporate, and this is the class of the metal organic frameworks. And there the situation is a bit different. So you have like huge organic molecules which connect to so-called like central atoms like metallic ions or like small metallic clusters. and then really build up these kind of 3 or 2-dimensional networks in space. So the interesting thing is that I realized that when I start to talk to chemists, they typically refer to metal organic frameworks as inorganic materials. But I, with my kind of naive point of view, saying like, okay, they first of all, they contain the word organic in their name. Second, they have the carbon compounds or the organic molecules involved. So that's like, for me, also kind of considered organic during my talk and also during our database. So what is so interesting about these materials? So one thing is that, like, if you go back, for instance, to the organic molecular crystals, you have like very, very different energy scales involved, namely that kind of electrons, which mitigate the binding of the atoms in the molecules, like that the kind of binding energy and the hopping within the molecule is much, much, much stronger than the hopping between the molecules. And that typically leads to like super flat electronic bands, which we will see in a second. Like if you calculate band structure of these materials, you will see that the kind of bandwidth of these materials is smaller compared to inorganic materials by at least the order of 10 or even like 2 orders of magnitude sometimes. And as we can relate the flatness of the bands to a like very tiny kinetic energy of the quasi-particle excitations, then we can say that like any sort of interaction which takes place between quasi-particle interactions becomes dominant. And this typically leads to the fact that we have these like very, very rich phase diagrams of the organics, which show all sorts of like many body instabilities into the superconductors, or some like metal insulator transitions into the magnetic phases. So there's a couple of examples shown on the right for like BDT, TTF based organics, where I just want to show like, okay, depending on temperature and pressure, for instance, like you already see various different phases on the superconductivity and different kinds of superconducting order. Or like below, you can see that the kind of emergent molecular magnetism in also like BDT compound under pressure, where you have like nominally non-magnetic molecules, which then in this crystallographic framework start to kind of polarize their magnetization due to the strong interactions. And due to this like super exciting physics which takes place in these materials, there's like a lot of applications of the organic materials. And like first and foremost, most dominant one right now is probably the applications in the organic LEDs, which are nowadays used in every smartphone or like every kind of TV display. So this is a billion-dollar industry kind of related to the identification and kind of implementation of organic materials for these sort of applications. But there's also like other things mentioned, like people discuss organics in connection to qubits, to spintronic applications. Like I mentioned before, also on the academic point of view, the spin liquid physics plays a dominant role, because like if you take a look at this picture on the right with the emergent magnetism, like you typically, as these molecules contain no magnetic atoms by themselves, they typically spin polarize with like magnetization of about kind of 1 mu Bohr. And then if you have like frustrated lattice, for instance, that one is kind of almost on the verge to that. But if you have this kind of triangular coupling between the molecules, then you start to set up like frustrated quantum magnetism in these materials. So let me just briefly mention like what we do. So actually, like when I came to know DITA about 4 years ago, like the first idea that we had was we actually realized that in the realm of the Dirac materials, like all the known materials at that time were inorganic. So people discussed topological insulators like the bismuth selenide or tin telluride, or the Weil semi-metals, which is like tantalum arsenide and others. But we realized that there's pretty much no coverage on the organics. So we thought like, okay, why don't we just take like, simplest approach, just try to grab crystal structures from where we can find them and do like the straightforward PVE VASP calculations of like maybe 1,000, 2,000 materials, and then we might get lucky and see like 1 or 2 examples, which we can discuss in more details. But then it actually turned out that, yeah, we found some examples and discussed it, but realized also like now we have some initial data, so what do we want to do with that? And then the natural idea is that like, okay, let's organize this in terms of like nice framework for the outside. And that's pretty much how the organic materials database evolved. So we initiated our framework, or like published it on our web page in beginning of 2017. And if you want to, you can kind of define like kind of 3 flags. One, which is kind of the largest and most kind of prominent in our database, is like our electronic structure part, that we calculate band structure and density of states of organic molecular crystals and metal organic frameworks. And we currently have a like data set of the about 40,000 calculated materials, which is just done in this like simple PBE approximation. But we are also like currently working on a kind of more evolved data set, taking into account like some meta GGA approach in connection to the van der Waals, and like setting up a bit of a more sophisticated data set. But then we also have the like part on the magnetic structure, which is much smaller, because like calculations are actually quite expensive on that, but where we calculate also like magnetic ground state, some of the materials, and like magnetic excitation spectra, and even like neutron scattering cross sections. And the third, which is maybe also interesting to discuss in this community, which is still on a bit premature state on our page, but which I actually find quite exciting, is that we also started to set up some sort of OMDB community where people actually can come like to each material page and say, for instance, like, I find this material interesting. Is there anyone out there who can synthesize this? Is there anyone out there who can do this or that measurement? Or is there anyone who can do a little bit more advanced calculations? You also can upload your own results. If you did like an experiment or something on one of the materials, then we even have some sort of referee system where if you upload your results, somebody is asked to check what you upload is some sort of meaningful. Is there like any, for instance, kind of peer-reviewed paper or like any sort of publication related to that, which explains how you got to that value? And we also have these things that you can start to follow materials, which we then can, for instance, use to automatically figure out what your interests are and suggest you with materials examples, which are, for instance, coming in when we calculate new materials. Let me just briefly show the workflow, which also gives me the opportunity actually to thank Solius, who initiated this COD. And I actually have to say that I'm a great admirer of this project, because it makes actually things very simple. And there's like insane amount of organic crystal structure stored. So what we do is we actually go to the COD, we calculate, we download pretty much, like at the beginning we started, for instance, to say like we download everything from journals like Organic Letters or something. But now we pretty much say like everything that contains carbon and hydrogen, and then some other atoms. We take that, process it with a like nice framework. We use this PyMarGen, and then we just produce our kind of VASP input files, run our calculations for the band structures, density of states, magnetic moments, and like other properties, and then we just dump it into our database. So that's pretty simple workflow. And let me maybe just, instead of just showing you some slides, show you how this database works. By the way, actually, I forgot to mention at the beginning, like if there's any questions or something, just let me know, because I think it probably makes more sense to have a bit of the discussion around this whole framework, and not only to have the kind of pure kind of talk broadcasting from me to you. So this is our web page. If you go to the omdb.mathhub.io, then you reach here. This is like our kind of landing page with some information about like kind of latest research and some papers that we wrote, which I might also address a bit kind of later during my talk, and some examples. And actually, most important thing, we are GDPR compliant. So we just want, we just want to put this thing up front to be very clear about that. So if you now go to the kind of browse materials page, we have currently like the about 38,884 results stored. And if I just click on one of the examples randomly, then this is like what we show. It's pretty like, let's say, in line with other materials databases. We have some like interactive view of the crystal structure. You can actually extend it by one click and see like how these materials kind of look in the three-dimensional space. Provide some additional information, crystallographic information, crystal density. So this is pretty much everything that we get from the COD. And we also reference like the COD ID actually for every material, but we additionally also have our own. And then we show the band structure and density of states. Everything's interactive. You can zoom in, zoom out, look how it looks. You can download input files for our VASP calculations. We have our flags for these community contributions where you can say like, now I want to add something here. I want to say like, okay, this I measure the band gap of this material or something. And let's see. And additionally, we show some sort of like clustering of our materials where we say like which other materials in our database are kind of similar to this material by crystal structure, or for instance by electronic structure, like the density of states or something. So we, for instance, focus on a kind of small regime of density of states around the Fermi level where the actual physics takes place in these materials, and say like what other materials might offer the same properties. So this is our kind of materials framework. But up to that point, I think it's not very kind of handy for like doing actual kind of identification of materials. So what we focused on was developing tools like how I can actually find information in our database. And one thing that we did is we have like our interactive search up here. So what you can see on the upper part of our page is a band gap distribution histogram from all the materials that we have. And you can actually see that there's kind of, it pretty much shows three features, right? There's like something which almost looks like Gaussian distribution of gaps, which kind of peaks somewhere between 2.5 and 3 eV. Then you have this part like below the 1 eV, which is almost kind of equally distributed. And then you have at 0 EV, you have the class of the metals. So let's say you come in and you say like you want to design a solar cell, then you can just click and say like, okay, for solar cells, I need a band gap between 1 and 1.5 EV. So you can select that part, and then you get like out of our 40,000 examples, you get the 1,500 examples, which actually have this feature. And then we can even kind of, for instance, add something on top. You can, for instance, say like you can show the same for the magnetism, and you want a material which is pretty much non-magnetic, then you can like, again, select the part which is non-magnetic and kind of narrow down this, this space. What I find also quite interesting is actually like a clustering. So we show a plot of a few examples.
Matthias, can I ask a question?
Oh.
So do you have a way to combine two things, let's say the magnetization and the gap, for instance?
Yes, yes. So they like you can, like it's always selective, you know. If you start, let's see. So it always kind of starts to set up these like subclasses. You can, for instance, start first, like you focus on a specific magnetization part, and then it shows you the band gap distribution of these 180 materials, and then you can say like now you focus on a specific part of the gaps, and then you can even like, you know, go further and say like now I also want to focus on a specific part, for instance, in the base group, and then you end up with one materials which okay. Shows you what you have.
Thank you very much.
Right. So now we go back, because I also want to show you one thing which I found actually quite interesting. And no, something is wrong with that button. Let me just reload this whole thing. Yes. Which I actually found quite interesting, because what I realized, which might be apparent to others before, but what I realized was like the moment that you start to kind of collect all this data, you suddenly start to ask like very different questions about this data and about the physics behind this data. So let me show you, for instance, one example, how you can kind of extract kind of very interesting information about the broader class of materials, right? Like, because one focus that we usually come in is that we say like, I want to have a material with a specific target property, but you can also do the opposite thing. Like the moment that you have statistics about the class of the organic materials, you can start to come up with very, very general statements, right? I can say like, for instance, kind of an average organic material has a band gap of 2.5 or 3 eV or something, right? And this is a highly non-trivial statement, which probably makes sense the moment that you start to think about it, why this is the case. But you wouldn't even ask this question, like, why does a material have this band gap, if you didn't know that kind of statistics shows you this, like this situation. So one interesting thing emerges actually if you take a look at the similarity of the crystal structure. So what we, for instance, do is take a crystal structure, define it as a kind of super, like highly dimensional vector. Then you can, there's certain ways how you can define kind of distances between vectors in this highly dimensional space. For instance, one is kind of via the sign matrix. And then you can start to kind of use dimensionality reduction algorithms. There's this like UMAP, or there's the TSNE, and it doesn't really matter. But at the end of the day, like you see a picture like this, where you project this like highly dimensional space of the crystal structures to the 2 dimensions, where these like 2 dimensions actually don't have any meaning. The only meaning that you have is that dots, which represent our crystals, which are close in the high dimensional space, are also close in this low dimensional space. So if we now, for instance, plot these kind of information of all the materials that we have in the database, then we see, for instance, features like this huge banana. And if I put like an additional property on top, like the band gap, then I see that this banana actually corresponds to a class of pretty much high gap materials. So I can say like, okay, let's just select a part in this banana and take a look how our band gap distribution looks for these materials. And then I see like, okay, actually like in this part, I pretty much get all the materials which belong to this like Gaussian band gap distribution that I've seen in my initial plot. And I have like about 1,500 materials. So it's also like a regime where I can say like, okay, it's large enough to say something about statistics. And if I take a look at these materials, then I see that all these materials are kind of pure organic molecular crystals. So there's no kind of transition metals or something involved. It's just like carbon, hydrogen, sometimes nitrogen, oxygen, maybe some fluorine or sulfur or something. So if I click on this material, then I see that my crystal structure is just composed of kind of individual molecules, right? And then I actually can come back to this point that I say like, okay, in these organic molecular crystals, like each molecule itself is already kind of saturated with electrons. Like each molecule itself is kind of stable unit, and they just interact with van der Waals interaction. And there's no reasons why kind of electrons would hop from A to B. So there's no reason why this material should be metallic, right? And then the band gap that we see is pretty much a random, like if you want, is pretty much a random quantity. And if you do this kind of, for instance, random matrix theory, then the level spacing between the eigenvalues and the random matrices follow this like Wigner-Dyson distribution. And this is pretty much what you see when you select this class of materials. And then we can do the same thing and can, for instance, say, so what if we go to our cluster graph and just select something which has a tiny gap? Then I get the kind of 600 or 560 materials. And if I now take a look, like all these materials contain transition metals, right? They contain the copper, they contain the manganese, the cobalt, and whatever. If I go to the gaps, then I see now I actually selected this first part of my gaps. And if I take a look how this comes, then I can actually say like in these materials, you have this kind of very, very kind of like these kind of atoms with very, very localized electrons. Like this, for instance, contains copper. Copper has localized d electrons. These localized d electrons, they also don't want to hop with their neighbors or something, but what they actually do is they get kind of influenced by the surrounding crystal field of the molecular linkers. So they start to split. So the gaps that we observe in this regime are all gaps which arise due to the crystal field splitting of the neighboring atoms. And this kind of crystal field splitting strength is of course kind of much weaker than the 3 eV or something, so that the gap sizes that you expect are pretty consistent. So this is just like, you know, to show how you can do or like deduce actual information about a huge materials class just from having data. And this even works if you have data which is kind of not performed in the kind of most efficient way or like most kind of sophisticated way, but which is kind of consistent, right? So the importance is that like every material of us is calculated in exactly the same way, right? So all the errors that we do in our computations, they constitute to the kind of systematic errors that we do. So in reality, probably this band gap distribution is maybe like a little bit thinner or thicker or like shifted to the left or the right, but kind of general physics should be the same. All right. So let me just ask, like, how am I doing in time? Like, because the talk was supposed to be 25 minutes, right? But we started a bit late.
Yeah, but there's no, okay, you can finish.
All right, because like I just have, this is, let's say, this was kind of most important part for me was to show you the database, but I also would like to show you a few examples of research that we did. Maybe one kind of an important angle to add to this whole discussion is that we, of course, also use our data to apply machine learning algorithms. So here is my kind of simple, intuitive way of understanding what my machine learning is. So you, for instance, like what we are usually interested in is we have a crystal and we want to have a property, the band gap or the magnetization density or the density of states or something. And we can like view this kind of calculation of this property or the kind of emergence of this property as a highly dimensional map or like highly nonlinear map between our crystal structure and this property. Nobody knows what this exact map is, but machine learning can help us to find a kind of approximate of this map. And the moment that we have that, we have like a very rapid way of kind of scanning through unknown materials, and it even allows for something like, since machine learning models are typically differentiable, it even allows for the kind of application of algorithms to find the sweet spots in our materials, like for instance conjugate gradient algorithms or something which try to find minima in some potential surface. So we can say that given a property that we want, we can reach that quite quickly, like using machine learning. So here's just like to mention, we have like one paper where we showed some benchmark on a organic molecular crystals data set with the gaps. So like on the lower left side, you see the distribution of a data set that we used for our training, and we just concentrated on the like non-magnetic molecular crystals. So on this like Gaussian part of our materials. And we have actually released this data set. So everybody who registers like on our page, which like everybody with an academic address, email address can easily do, can go and download our data set and can do whatever she or he wants with this data set. And what we show is that, for instance, applying kind of the standard machine learning methodology, which is available right now on this data set, you like reach, for instance, an efficiency like of a mean absolute error of the 0.36 eV. So if you say like that the kind of average band gap of this data set is about 3 eV, your error is about 0.3 eV, then you're kind of wrong by 10%. Like it's probably not a very that's rigorous way of defining the accuracy, but it's a like intuitive way. And in most cases, this is good enough. But for instance, if you take the same methods and apply them on the single molecules, they perform much better. So like for both the SOAP and the SCHNET that we used as an example for the kind of training, I think they show it on these like QM9 data sets, something that they can reach chemical accuracy for specific properties. But the moment that you go to actual periodic crystals, the situation is actually way, way more challenging. So in some sense, like with this paper, we invite others to try themselves and maybe come up with smarter ways of.
How many data is there in the data set?
In the data set, it's just 12,500.
Okay. It's already a big data set, yeah? So interesting.
I think it is okay. The tricky part of this data set is that the materials themselves are typically highly complex. Like an average, like our materials in this database have the 86 atoms in the unit cell. And that makes it actually quite demanding, I think, to cover this space, right? Because like you have some variation about the number of atoms, you have some variation about the kind of local frameworks. And one big problem that I see is that, for instance, like pretty much all the methods that I'm aware of which exist to map the crystal structure into a descriptor of the machine learning model, they are pretty much kind of focusing on local properties, right? They say something like, you know, you take an atom, you make a kind of huge sphere around that and incorporate all the information of all the surrounding atoms, and then you construct something out of that. But it's probably a good approach to predict local properties, like what is the kind of charge density around a specific atom or something. But something like the band gap is a kind of global property of a material, right? And I'm not aware of any way of putting the of kind of really using this like periodicity condition that you have in the crystal to set up a descriptor for the machine learning model. So I think that would be actually a quite interesting thing. So what we also do is like we for instance, for this machine learning example, we implemented a small app into our database where people can upload their CIF files, and then they get the predictions like within a few seconds. And then of course we can we plan to extend this for the other properties that we have in our database. Let me just show you a few examples like what we did. As I said at the beginning, we were interested in finding these Dirac materials. So these are materials which effectively show this kind of fully relativistic dispersion relation of the quasi-particles. And if you have the kind of massless situation, if you say like this is your energy function, you say set the m squared term to 0, then you see the kind of linear crossing in your band structure, where for instance prototype material is graphene. But it doesn't only have to be on the pure electronic side. It can also be like, for instance, D-wave superconductors or liquid helium, which kind of show similar excitation spectra. But like we were interested in finding these crossings in electronic band structures. So what we, for instance, did is we implemented similarity search tools to find actually linear crossings in our band structures. So actually, let's see, it should even work online. I haven't tried it in a while, so this is interesting. So if you go to our page, then you can search by patterns. So we provide specific examples, for instance, the linear crossing or the two parabolas, but you can also draw your own thing where you just put a couple of dots and then it connects it in some way. And then you could search, for instance, for these sort of patterns in our band structures. But let's take the example of the linear crossing, for instance. We say like we don't need that. We put the distance of the bands very small and search. Let's see what we get. Then it performs a kind of live search on our database and gives us 40 examples of materials. So if we click on one of them, then it highlights the part where it finds the crossing. So if we zoom in, then you see that the algorithm kind of identified some sort of mass where bands cross linearly. So there's probably like other examples in the same material which are picked up in the other search results that we have. So let me show you one example where this actually had been quite interesting. And this was when we kind of started discussing with local experimentalists here at Stockholm University. So there's a huge group which is actually interested in the detection of dark matter particles. And to my best knowledge, as I can say, like, I mean, nobody knows what dark matter is. So that's the big puzzle that we have. We just know that it kind of constitutes to kind of huge amount of the mass that we observe in astrophysical observations. So they claim it's about like 90–95% or something of the mass is pretty much unclear what it is. So what people started to come up with over the years is they say like there might be like elementary particles connected to that we are not aware of yet, which might decay into this kind of standard model particles or something. And there are kind of different theories like how these particles could behave, and the kind of simplest way that you can do is you can say like, let's say your dark matter particle is a vector boson, and then since you want to have it massive, then you kind of write down a Lagrangian where you have a kind of massive vector boson with a kind of kinetic term which is this kind of field strength tensor F mu nu prime, and then you can, for instance, couple it to a particle in the standard model like the electron, which couples to its own gauge field, and you say like, let's say there's a mixing of the gauge fields of the electron and of the dark photon, some sort of unknown process and a very, very small coupling constant, and can calculate kind of depending on this like tiny strengths of this constant, how this kind of dark photon, for instance, something would affect kind of our electrons. And there's a kind of nice way of measuring this. If you say like, what if we take a material which actually effectively behaves as a fully relativistic electron, which brings us back to our Dirac materials, and say like, okay, take a Dirac material, go to the case where you have a tiny mass in the range of the kind of kinetic energy of the dark photon that you want to observe, which you actually can estimate from kind of astrophysical knowledge, that you know kind of what is the escape velocities, for instance, out of our galaxy or something. And then you can say like, okay, what is the kind of strength of measuring this particle? And one thing that we, for instance, did is like we tried to mine for materials which might be of relevance for this process in our database, and came up with a couple of examples. And one of them is, for instance, this BDT TTF BR-based compound, where you see these like nice linear crossings at the Fermi level. And these crossings can, for instance, be found quite easily with these pattern matching algorithms, which I showed before. So if you're interested in that, like there's kind of two contributions that I did. Like one is on the actual theory, how this process works with measuring dark photons in the Dirac materials. This is our PRD, and there's a kind of earlier paper by Jonit Hochberg before. And here's like our kind of materials informatics approach to this, where we show like how you define kind of specific properties that these sensor materials should have and how you can find them in our database. And then like, let me finish with a last example. There was actually like quite interesting paper a couple of years ago, which also introduced a lot of the controversial discussions in the field of the organic materials. And this is a paper about the high TC organic superconductors. So superconductivity in the organic materials is actually a known effect, and it occurs in these cases where you actually have the conducting organic molecular crystals. As I said initially, like you have a tiny bandwidth, so you have strong interparticle interactions, and there's kind of mechanisms how you can, for instance, generate the superconductivity in these materials like for instance, in terms of something like a Hubbard model, out of the kind of fluctuations of some, for instance, magnetic ground state. But the typically observed transition temperatures in these materials are in the realm of the like 10 Kelvin or something. So there was a group in China actually, which took a kind of superordinary molecule, which is p-terphenyl, which you find in every sunscreen and like, yeah, which you can just easily buy on any kind of chemical platform. And they mixed it kind of heavily with potassium, put it in the oven, baking it, and measured kind of a Meissner effect on that, because it's very tricky to attach electrodes to this. So they measured the Meissner effect and saw the drop in the magnetic susceptibility at the 120K. So this is a kind of massive, this is a huge number. And then of course people said like, okay, it's not really clear what is happening. Like maybe this is like all made up and so on. But like during the past years, we see that there's kind of more examples coming up. And I actually talked to one chemist who said like the way that they synthesize it, they completely destroy all the information of the molecule. They just end up with a kind of complete mesh of carbon and potassium, and that might be the superconducting thing. But anyway, what we thought is like before one even comes up with some sort of reasoning about what's going on, it might be better to find more examples. So we can, for instance, do the simple electronic structure calculation of this material and compare it to all the materials that we have in our database. And then we came up with some suggestions of organic molecules which might behave differently actually. And we also started to kind of collaborate with some of the research groups actually in China. And I know that at least for one or two, they kind of see similar effects, not necessarily in the range of the 123K, but kind of applying a similar synthesis strategy. They see the kind of drop of this magnetic susceptibility at some some temperature, which is actually quite interesting, I think, and which is a like new approach that one can provide. So with that, I think I said enough for today.